Today we are going to solve the question 8. Here the first question we have already seen in the lecture. We will solve the B and C. The B and C is very important from the perspective of quantum mechanics. So let us solve the question B. In question B it is asked, so that the equality sign in the generalized uncertainty relation hold if the state in question satisfied. Delta A, alpha, lambda, delta B. Delta P is the dispersion of the operator delta B, and delta is the dispersion of operator. Now, if these two dispersions holds this relation, then the equality sign of the generalized uncertainty relation will be true. So what is the generalized uncertainty relation? That is delta A its square and its expectation value into dispersion square, and its expectation value should be greater than equal to 1 by 4 expectation value of commutation between A and B its square. So let us check that. To check this equation, come from the most general form of the uncertain relation. The most general form of the uncertainty relation. What it is? It is delta A its square, delta B its square should greater than equal to modulus of delta A, delta B its expectation square. We get it from the Schwarz inequality. We get it from the Schwarz inequality, this inequality. Now, this is the most general form of uncertainty. Now we can express delta A comma delta B in terms of delta A into delta B, delta A into delta B in terms of, as we have seen previously in lecture, delta A delta B plus half anti-commutation of delta A comma delta B. And we have already seen that this is nothing but half A comma B. Now let us prove if this relation holds. That means if this relation holds, delta A alpha is equal to lambda delta B alpha, where lambda is a pure imaginary number, then this will be equal. That means if it is happens so, delta A its square, delta B its square is equal to 1 by 4 expectation value of commutation relation A comma B its square. So let us first calculate the expectation value of delta square. Now calculate delta A square alpha. So alpha delta A alpha So if we operate this relation holds, that means this relation holds, then if this relation holds, that means this will be alpha delta A lambda delta P alpha. Now this is actually the dual correspondence of the delta A alpha, which will be, if it is lambda delta B alpha, then its dual correspondence will be lambda star delta B alpha, sorry, lambda B lambda star alpha delta B. This is actually delta B. It's actually delta B. So that means this is equal to alpha lambda star lambda delta B square alpha, which will be lambda mod its square alpha delta B square alpha. That means delta H square into delta B square expectation will be lambda square delta P square's expectation its square. Now let us calculate the expectation value of these two things. Now expectation value of alpha delta A delta B alpha is equal to alpha delta A delta B alpha minus alpha delta B delta A alpha. So again it is nothing but lambda star alpha delta B alpha, it is minus alpha delta B lambda delta B alpha. Now if this lambda is pure imaginary, that means lambda star will be minus lambda, then it will be minus lambda alpha delta B square alpha minus lambda alpha delta B square alpha. That means minus 2 lambda expectation value delta B square. And what is the expectation value of the anti-commutation between this? That will be 0. Let us prove that. So expectation value of the anti-commutation delta A delta B, and here this delta A and delta B are Hermitian. We have explicitly assumed that's why this the correspondence of A B alpha is actually the dagger, since this is Hermitian, so that's why we explicitly assume it is equal to B. So now alpha delta A delta B alpha plus alpha delta A delta B delta A alpha. So here again it is lambda star alpha delta B square alpha plus lambda alpha delta b square alpha. Since this lambda is pure imaginary, that means it is nothing but minus lambda delta b square expectation plus lambda delta b square its expectation. So this will cancel, it will keep 0. That means from the relation, that means the expectation value of delta a delta b will be half expectation value of a delta b. Now what its value? Its value is half into minus 2 lambda delta b its square. Now what is the expectation value? What is then what will be the what will be the uncertainty relation? The uncertainty relation will become delta h square delta, what is the delta square into delta b square? Delta square into delta b square is nothing but lambda square delta square square. So now delta a square its expectation delta b its expectation is equal to lambda square delta b square expectation. And what will be the expectation of this delta a delta b its square expectation square? That will be again lambda square delta, here it is square, so lambda square delta, here from here delta a delta b square is equal to lambda square delta b square its square. So from here also, that means from these two relation we get that delta square into delta b square is equal to expectation of delta a delta b its square, which is nothing but we have seen that it is equal to half of expectation value of a comma b its square, and expectation of anti-commutation is already 0, that means is equal to 1 by 4 mod of expectation of a comma b its square. So we have seen that if this relation follows lambda alpha where lambda is pure imaginary number, then the equality corresponding the generalized uncertainty relation holds. So that we have seen. Now we will solve the question number C. Here it is asked the explicit calculation using the rules of wave mechanics so that the wave function for Gaussian wave packets. So this is a Gaussian wave packets. So using the rate that this state satisfy the minimum uncertainty relation, prove that the requirement that how can we state that the uncertainty relation in this state is minimum, that is the equality relation hold. That means when this dispersion of delta a and delta b are follow this relation, that means delta a operator on alpha will give lambda delta b delta a, where lambda is a pure imaginary number. So if we general prove that delta x prime delta x alpha is equal to imaginary number x prime delta p alpha. That means that is actually equivalent to, say, that means if we can prove that delta x prime alpha is equal to some imaginary number into x prime delta p alpha, that is equivalent to, say, delta x alpha imaginary number delta p alpha. As we know that if this relation holds, then in the state alpha the uncertainty relation corresponding to the x and p operator will be minimum, that is the equal sign of the uncertainty relation hold. Let us check that this relation actually holds on that same state. So to do so, first write the first equation, which is x prime minus delta x means x minus average of x, that is expectation value of x alpha. So which is x prime x alpha minus x prime alpha. If we operate this on this state, this will give x prime alpha x prime alpha x prime x multiply by x prime alpha. Now let us calculate the other thing, that these things, x prime delta p alpha, which is equal to x prime p alpha minus average of p x prime alpha. From our lecture where we study that the representation of the momentum operator in position basis, we know this is nothing but minus I h cut del x prime alpha minus p x prime alpha. So let us calculate the what is the del x prime alpha, and it is given that x prime alpha is equal to 1 by root over of 2 pi. Let us check again what is its value. 2 pi d to the d square to the power minus 1 by 4. So that means it is 1 by 2 pi d square to the power minus 1 by 4 exponential of minus I p x prime by h cut plus let us again see that what is this, minus x prime minus mod x by 4x square, right? That means this is plus and the second term is minus, so this term is minus x prime minus expectation of f its square by 4t square. So let us check what is the value of del x prime. It will be del x prime x alpha, it will be 1 by 2 pi t to the power t square to the power minus 1 by 4 exponential I p x prime by h cut minus x prime x 4t square its square into multiplies I p x prime by h cut, sorry, there will be no h cut, is del x minus 2 means x prime minus expectation by 2 t square. So this is nothing but I p by h cut minus x minus expectation of x by 2 t square into x prime alpha. So what is the value then? X prime p alpha, which will be minus I h cut del x of x prime alpha, that is nothing but minus I h cut I p h cut minus x prime x by 2 t square x prime alpha. That will be expectation of p minus plus I h cut by 2 t square x prime minus expectation of x to x prime alpha. Now let us check what is the value of this. This will be x prime delta p alpha is x prime p alpha minus x prime alpha to average of p. So if we subtract, that means delta p plus I h cut to t square x minus x expectation into x prime alpha minus p expectation alpha. So this term and this term will be cancelled. That means I h cut by 2d square x minus expectation x prime alpha. But this term is actually, we have calculated already, this term is actually this. That means I h cut by 2t square into x prime delta x alpha. That means x prime delta x alpha is equal to 2d square by I h cut x prime delta p alpha. That means this lambda, this constant is pure imaginary. That means the delta x alpha is equal to 2d by I h cut delta p alpha. This relation holds. That is actually means that the uncertainty relation, that is delta x square delta p square, its expectation will be equal to 1 by 4 the square of expectation of x comma p h square. As we know that x comma p is nothing but h cut by 2 h cut, that means that will be h cut square by, is this is equal to h cut, we know that this means h cut square by 4, and this is, that means delta x square its root into delta p square its root equal to root over of h cut. So h cut by 2, that means root over of delta x square its expectation delta p square its expectation is equal to h cut by 2. So in this state alpha, the uncertainty relation relation corresponding to operator x and p is minimum which is equal to h cut by 2, and alpha is the, we know that, Gaussian wave packet. So that is that. Thank you.